no, it may be some problems with the internet. I do not know whether it happens or not, but as it seems to me, I can push on my camera and to turn on my face. But okay. First of all, good day, everyone, and good day, my dear colleagues. Today I will talk about a very interesting theme as for me. Of course, my name is Zakhar. I am an employee of the Institute of Theoretical and Experimental Physics, as well as the Moscow Institute of Physics and Technologies. Today's report will focus on the problem of chiral effects and their emergence in QCD. I need to admit that the concept of chiral effects means the emergence of non-dissipative currents in the sense of external fields in thermodynamic equilibrium. The description of this term will require more than one presentation, so I will focus on the most significant for me effects and features that I find to be the most interesting. I also want to admit that tomorrow will be a very interesting talk of Valentin Ivanovich Zakharov. He is one of the most interesting members of community of chiral effects. That means that I think it is. I will not try to absorb all concepts of the chiral effects. So. The most interesting features of chiral effects, as it seems to me, are, first of all, the possibility of existence of currents in equilibrium, connection with responding anomalies, and sensitivity to interactions. On my talk, I try to consider the chiral magnetic effect, that is emergence of electric current directed along magnetic field in presence of axial chemical potential. I will talk, of course, about chiral separation effect. That is the emergence of the axial current directed along magnetic field in presence of vector chemical potential. And I try to say some words about chiral vortical effect. That is axial current that directed along vorticity in presence of temperature, for example, chemical potential or acceleration, and it is interesting that without this terms, it is enough vorticity to observe chiral vortical effect. We can present a universal scheme for such an effect. First of all, if we have left particles interacting with the field run in some direction, and right particles interacting with the field also run in some direction, all we need to create is zero density of such a particle. So that is universal scheme for the chiral effects. First of all, we need to define the sequence of steps by which we will describe chiral effects. First of all, we need to say that there are many approaches to describe such an effect. The study is carried out with the frame, for example, of an effective series or computer modeling. But we will be most interested in the microscopic description of such a phenomenon. This is because we calculate all the quantities in the theory from the first principle without any additional assumptions that can be non-physical. Also, we always must use regularization to obtain final answer, and we need to point out that even ordinary thermodynamics may also contain divided divergences. I guess this statement will be very important for me in my talk. Very often one can find the opinion that the chiral separation effect and the chiral magnetic effect are twin brothers, as you can see from the formula on this slide. And indeed, as we see, the expression of currents are very similar and obtained from each other by replacing the axial chemical potential with a vector one and vice versa. In non-regularized theory, an excess of axial charge in thermodynamic equilibrium in an external magnetic field induces a vector current. That is the first formula on this slide. and an excess of vector charge induces an axial one. This is the second formula on this page. I need to point out that all of these statements need to be accurately transferred to the theory with regularization. As we remember, when we take into account quantum ethics, classical symmetries can be violated. This phenomenon we usually called anomalies. I guess historically an anomal non-conservation of current was discovered by Schwinger in early at the beginning of the 1950s, I guess. But I think that, for example, Adler wrote that this is not quite correct statement. In the model of two-dimensional quantum electrodynamics, Schwinger observed chiral anomaly. And in this case, it appears most clearly. We have, for example, we have two currents, which is the classical level are conserved in the massless limit. As soon as we consider quantum field theory, we have an alternative. Which of the two currents should be conserved? If we conserve, for example, the axial current, then we have to violate the vector current. If we conserve the vector current, then we have to violate the axial. There is a similar problem in 4 dimensions. We may say that there is no regularization of quantum field theory which would allow to conserve the axial current. At the same time as all other currents in the theory are conserved. So I let myself this excurse in order to explain why the chiral separation effect and chiral magnetic effect are not twin brothers. First of all, it is worth mentioning that even with the naive calculation, without taking into account regularization, it can be shown that the chiral magnetic effect does not depend on mass. It's very interesting statement, but it is in case of chiral magnetic effect, one can calculate it directly. But for example, in case of chiral separation effect, the effect is very sensitive to the mass of particle. In other words, the heavier the fermions, the weakest current, and in the case of infinite mass, there is simply no effect. Thus, this remark, I guess, allows us to formulate a very interesting statement. As we remember, Pauli-Willis regularization is allowed in quantum field theory. We need to consider the expression for current and subtract the regulator contribution for infinite mass. In the case of the chiral separation effect, we subtract 0 due to the fact that the CSE effect is rather sensitive to the inclusion of the mass. But in the case of CMB, we recall that the effect does not depend on mass, which means we obtain 0 current in well-defined theory. Of course, all of these calculations were done explicitly. For example, in the work of Pavel Vasilyevich, he was found on the lattice that the chiral magnetic effect should vanish. You can see his result on this slide, and on the graph, one can clearly see that the electric current turns to 0 as a function of the external momentum, that is. For example, that's the ideal case, and after that, Pavel Vasilyevich tried to calculate polarization tensor for vector-vector contraction, and after that, he obtained that at the 0 momentum limit, nothing happened. So the latest proof to us that there is no chiral magnetic effect in thermodynamic equilibrium, and I guess that it is a correct statement. But let's also try to argue that the chiral separation effect and the chiral magnetic effect are fundamentally different. Oddly enough, significant difference appear when one considers system with the boundary conditions. That is very interesting exercise. And for example, Miransky and Kolassos, that is the name of the book, perform calculation for the axial and vector currents, taking into account the boundary condition of Bogolubov-like type along that axis. And they came to the very interesting conclusion that there is no mode that should saturate the vector current at non-zero axial chemical potential. And that means that there is no chiral magnetic effect in this case. While the current separation effect you can see on the slides, there is exist, and in continuum limit, it turns out to the standard expression. And the result is presented on the graph from this paper. That is, for example, the axial current in massless case. They also calculated this density in case of finite fermion mass, but they obtained nearly the same results. I also want to point out that it is also worth mentioning a series of papers by Mikhail Alexandrovich Zubkov on the topology of momental space on the lattice, within which it was shown that there is no equilibrium chiral magnetic effect also. So we understand something important for CME case, but we need to use our knowledge for investigation of CSE effect. So few words about CSE. I guess, and with this knowledge, let's move on the chiral separation effect. I have said that one of the questions I'm interested in is the relationship between chiral effects and the corresponding anomalies. That is interesting questions for all effects. For example, that is also a very interesting question for chiral vortical effect. But on the contrast to the chiral separation effect, it postulates that chiral vortical effect in some sense is connected with gravitational anomaly instead of simple axial anomaly. In the case of chiral separation effect, the relationship would seem to be easiest to detect, I guess. And indeed, we have the axial currents as in the expression of chiral separation effect. We can get the expression for the axial anomaly in Susskind's manner. I.e., we just need to turn on the electric field, and count the number of transitions from left particles to the right, and after that we obtain that in this case we may say that the coefficient in front of the magnetic field mu divided by 2p is associated with the anomaly. Here comes a very intriguing possibility, if so, of course. If the coefficient is really associated with the anomaly, this means that we have the opportunity to introduce some kind of top matching conditions in the media. Once again, if so, we have non-normalizable, observable effect in QCD that is directly connected with the axial anomaly. And as it seems to me, for experimentators and for experimental observation, it is very intriguing, intriguing possibility. But why it can be true also? I want to focus on Zakharov's statements about connection of CSE with the axial anomaly. That means that if we take the derivative of the chemical potential with respect to spatial coordinates, that leads to the electric field, and we reproduce the expression for the anomaly simply to differentiate the expression of the current. Moreover, as a confirmation of this version, we can try to calculate chiral separation effect in case of high spin theory. And this possibility was really considered, including by me and my colleague, Ruslan Abramchuk. We have considered the theory for spin equal to 3/2 normalization theory. In some sense, it is well-defined theory. And in this theory, it is possible to calculate both the axial anomaly and the chiral separation effect. And it is very interesting that we obtain these results in two cases. In the first case, this is a real relativistic theory for spins 3/2, and in the second case, that was just a theory that describes for the particle in Rita-Schwinger well semimetals, and in these semimetals, there may also be some analog of an axial anomaly. I also want to point out the paper of Zakhar, Chiral, and Prokhorov, in which the chiral vortical effect was calculated for real relativistic theory with a spin 3/2. This is not CSE, of course, but the work is very impressive and worth mentioning. Once again, why we made this statement be true about connection between the chiral separation effect and the axial anomaly. if you recall, for example, the paper of Dolgov and Zakharov, it was the paper of 1917, I guess 1972. In this paper, the axial anomaly can be calculated at any scale. So in the medium too. However, neither the chemical potential and temperatures nor the percents of the medium affect the coefficients before the product of the electric and magnetic fields. And for example, if we take into account the mass of fermions, this also does not affect the result. But we can also argue that the coefficient before the anomaly does not determine the coefficient before CSE. Why not? First of all, a different behavior in presence of any mass of fermions. At low temperatures, the chiral separation effect is intimately connected with the Fermi surface, while the anomaly can be calculated on any scale. Here it is worth stopping a little and mention a very important paper that the results of which we must to explain. The fact is that the chiral separation effect can be observed on the lattice or calculated on the lattice, which means that we have a numerical experiment. It is very important for us. I guess maybe I will talk about this a little bit more intensively, but Pavel Vasilyevich Buividovich and Pur and his co-author find some fingerprints of the anomaly in the massless case. That is the work of Pavel Vasilyevich. He published it in 2017, but the most emphasizing fact was that there is that they calculated the chiral separation effect for massless fermions, and as you can see from the graph, this one and the next one, no correction as a result of interaction to the effect observed. This is the just line. That's also just line. And this is, for example, their calculations for temperatures above critical temperatures. So I guess in the confinement phase. And they find that this effect depends only on the chemical potential. Let's try to understand some features of their calculations. We see that the results do not change depending on the temperatures, first of all. Here it is worth mentioning a very important point. Usually, in the literature, of course, there are no investigations for the influence of path transitions on the chiral separation effect. But from the point of view of lattice calculation, you can see it on on my slides. We see that there are no influence in the massless case. We see that there are the same graphics in the case of low temperature phase and in case of above critical temperature, they obtain the same results for chiral separation effect. There are some steps that we need to explain from a theoretical point of view. First of all, let's confirm the existence of chiral separation effect in thermodynamic equilibrium. And the strong interactions turned out to be not so strong to change this effect in the massless case. The second one, the fast transition has no influence on the effect. We do not see any effect of temperatures, either as, for example, some additional terms were connected with the chemical potentials, etc., etc. And we do not understand what degrees of freedom are saturated chiral separation effect, and for example, in pionic phase and in QGP. So we need to find some method within the framework of microscopic theory that will allow us to simultaneously obtain an expression for the axial anomaly and expression for the chiral separation effect. Only in this case we'll be able to answer the question of the extent to which the axial anomaly fixes the coefficient in the chiral separation effect. In ideal case, of course, we need to be able to answer the question of the extent to which the axial anomaly, in extent to which the axial anomaly fixes the coefficient, the chiral separation effect, of course, and ideal case, we need to consider influence of interactions. But from our point of view, it will be enough to obtain the coefficients of in case of temperature, final mass, and chemical potential, and show that they do not affect, for example, in case of the anomaly, axial anomaly, and they do affect the coefficient in front of chiral separation effect. For example, in case of fermions with mass. So we try to use also the following argumentation. If we show that the axial anomaly does not change and the chiral separation effect depends on mass, for example, and temperature, that talking in this case, the talking about the universality of relationship is too self-confident, I guess. So let's try to do all calculations in framework of the point splitting method. First of all, why point splitting method? The point splitting method was investigated quite a long time ago. Its important feature is the ability to calculate both the ordinary axial anomaly and, for example, the gravitational anomaly. I guess one can remember works of Nielsen at Schroer, etc. They obtained their gravitational anomaly in case, for example, of fermions with a spin of 3 so for us, it is extremely important feature is the ability of this method to separate ultraviolet and infrared scales. I need to point out that in this method, the axial anomaly usually is associated with the ultraviolet scale, and the chiral separation effect is associated with the infrared one. I also need to point out that in this method, the ordinary anomaly itself is connected with the flow through an infinite distance three-dimensional surface in momentum state. This fact is easily proven, and it means that this distribution of Fermi or any other effects associated with the presence of the medium can contribute to the coefficient in the anomaly. Moreover, it is easy to show that the presence of mass doesn't change the value of the coefficient before the product of the electric and magnetic fields. And this method is very easily to generalize to space with a dimension other than 4. And you can even prove that even show, I guess, that there are some protections against some type of interaction. I guess you can see, for example, some old paper of the Jacob and Kurchatov. So few words about the point splitting method. I guess that I need also to say that it is a method that can be calculated, for example, in case of Matsubara formalism without any needness to go to Minkowski's space. But I think that it is, I will talk about that a little bit later. So the essence of the point splitting method is that the expression for the axial current is extremely singular in the limits of small distance. To make theory well regularized, instead of an expression for a current defined at the one point, so it is just a simple expression psi bar gamma gamma phi psi. Well, we use some other expression that is in the limit of short distance gives an expression for the simple axial current. That is. And also we need to use a parallel transporter in this case, and it is usually enough to consider the expression given on the slide, taking into account that the expression for a parallel transporter looks in the following form. I also admit that we also have an opportunity to take into account the mass. So here we have a very interesting alternative. First of all, as I have said, we can make all calculations directly in Matsubara formalism. This formalism makes it possible to take into account interactions in self-consistent manner. Another interesting possibility is to calculate all quantities in so-called real-time formalism. This method is the most interesting for us at this stage, since I really wanted to rely on the already known results. We try to calculate for this expression in case of when the parallel transporter in my electric magnetic field is looked like on this slide, and after that we obtain the following results. Try to talk about that. First of all, as expected, exclusively ultraviolet part of the propagator is responsible for a coefficient in the axial anomaly. It is completely fixed from condition that the short distance space in Minkowski space, and that it is it is essential ultraviolet effect. It is worth noting that the Matsubara formalism, in case of Matsubara formalism, of course, I would simply say that the short distance, this space is just a Euclidean space. It is very important statement for us that the ultraviolet part of in quantum field theory and in fine temperature field theory coincide. Our remark is that the ultraviolet part in Euclidean space and in Minkowski space also coincide. A very interesting feature of this method is that the imaginary time formalism is actually equivalent to temperature, and thus the expression used for regularization of all expression in some sense is determined by the Gibbs distribution. As we expected, anomaly does not depend on temperature, or chemical potential, or on mass, but the Chiral separation effect turns out to be very sensitive to the inclusion of these parameters. In this method, we actually say that the Chiral separation effect is a density of effectively one-dimensional fermions at the lowest Landau level. Detailed consideration allows us to formulate the statement that the Chiral separation effect is also sensitive to the inclusion of interaction. To make sure of this, we need to have a model, for example, that is our results. For example, that we obtained the divergence for the axial current. And for example, we obtained also, I want to point out that we obtained the expression for Chiral separation effect at zero temperature. If we try to, for example, consider non-zero temperatures, the answer will be much more, to obtain the answer will be much more challenging question. So, to test ourselves and to make sure that our results is correct, let's try to look at the model with Lagrangian, which is shown on this slide. It's an ordinary interaction of UK, which leads to the fact that fermions get a mass from the interaction. And so if we play with lambda, for example, new h constant, we can show that the theory is extremely sensitive to changes in this parameter. The anomaly is insensitive to such manipulation just because it is ultraviolet phenomenon, and nothing better can happen in the ultraviolet diapason. But we also need to test our arguments independently from the point of view of the Latin calculation. In this regard, we are very fortunate that it is a work of Vasily Puidodochky, I guess, a very famous man in this domain, that calculate of quantities and try to investigate the Chiral separation effect in the case of QCD with massive quarks. I try to show the reference on this work on the slide. As one can easily see, the Chiral separation effect undergoes very strong correction. That is, for example, I can show on this slide that is this line is the standard expression for sigma CSE, that is nc over mu divided over 2 p square, and after that, in case of lattice, for example, then try to use different lattice sizes to imitate different temperatures, and observe that in case of real QCD, not a massless QCD, but a real massive QCD, this expression is very sensitive to inclusion of mass, and the color separation effects only in case of, for example, extremely large temperatures or extremely large chemical potentials will be close enough to the standard expression. I mean, mu over answer divided over 2p square. So it seems to me that I must to make some statements, and I try to summarize it in our results in relation to the color separation effect. So what we understand now. First of all, the mechanism of protection against corrections is different for the axial anomaly and chiral separation effect. We can clearly show that in non-interacting theory, the existence of an axial anomaly follows the existence of the chiral separation effect in all theories. While accounting for interaction is a very difficult task, in general case, we cannot say that that interaction is insensitive to CSA or CSA is insensitive to interaction. That's we need that we observed in case, for example, of real QCD and in case of our theory. So there is the problem of dependence of the chiral separation effect on fast transitions that remain extremely urgent. Excuse me. This problem is preliminarily relevant from the point of view of solid-state physics, just because the number of systems in which quasi-chiral fermions exist in this case are much larger. Very interesting thing for us, it is possibility of observing a similar effect in quark-gluon plasma or a simple QCD. As can be seen from the latest simulation in real QCD, the effect is quite sensitive to interactions. Therefore, purely theoretically, of course, it can be observed. But the question of quantitative description of this process is very important for experimental observation, this effect in the quark-gluon plasma. And almost last thing that I need to say that that can be mentioned in this section is that the point splitting method is a good platform for studying the relationship between anomalies and the corresponding chiral effects. That's also the case of chiral vortical effect too, because point splitting from the view of point splitting method, we can calculate the gravitational anomaly directly from, for example, fermion propagator. And I already mentioned about Nielsen and Schreier work, and thus it is, I guess it is very interesting to test this possibility of a case of chiral vortical effect. I guess that I talk enough, and so thank you for your attention, and if you have any questions, I try to answer them.
Okay, thank you. Are there any short questions to Zakhar? If not, then we move to the discussion session.